And data mining, association rule learning, is a popular and well-researched method for discovering interesting relations between variables in large databases. It is intended to identify strong rules discovered in databases using different measures of interestingness. Based on the concept of strong rules, Rakesh Agrawal and others introduced association rules for discovering regularities between products in large-scale transaction data recorded by point-of-sale (POS) systems in supermarkets. For example, the rule found in the sales data of a supermarket would indicate that, if a customer buys onions and potatoes together, he or she is likely to also buy hamburger meat. Such information can be used as the basis for decisions about marketing activities such as, for instance, promotional pricing or product placements. In addition to the above example from market basket analysis, association rules are employed today in many application areas including web usage mining, intrusion detection, continuous production and bioinformatics. As opposed to sequence mining, association rule learning typically does not consider the order of items either within a transaction or across transactions. Definition. Following the original definition by Agrawal and others, the problem of association rule mining is defined as, let be a set of binary attributes called items. Let be a set of transactions called the database. Each transaction in has a unique transaction id, and contains a subset of the items in. A rule is defined as an implication of the form where and the sets of items, for short ITEMSITs, and are called antecedent, left-hand side or learn-out and house-piece speech products, and consequent, right-hand side or RHS, of the rule respectively. To illustrate the concepts, we use a small example from the supermarket domain. The set of items is, and a small database containing the items, 1 codes presence and 0 absence of an item in a transaction, is shown in the table to the right. An example rule for the supermarket could be meaning that, if butter and bread are bought, customers also buy milk. Note, this example is extremely small. In practical applications, a rule needs the support of several hundred transactions before it can be considered statistically significant, and datasets often contain thousands or millions of transactions. Useful concepts. To select interesting rules from the set of all possible rules, constraints on various measures of significance and interest can be used. The best known constraints are minimum thresholds on support and confidence. The support of an ITEMSIT is defined as the proportion of transactions in the data set which contain the ITEMSIT. In the example database, the ITEMSIT has a support of, since it occurs in 20% of all transactions, 1 out of 5 transactions. The confidence of a rule is defined. For example, the rule has a confidence of in the database, which means that for 50% of the transactions containing milk and bread the rule is correct. 50% of the times a customer buys milk and bread, butter is bought as well. Be careful when reading the expression. Here sup, xi, means support for occurrences of transactions where x and y both appear, not support for occurrences of transactions where either x or y appears, the latter interpretation arising because set union is equivalent to logical disjunction. The argument of is a set of preconditions, and thus becomes more restrictive as it grows, instead of more inclusive. Confidence can be interpreted as an estimate of the probability of finding the RHS of the rule in transactions under the condition that these transactions also contain the learn-out and house-piece speech products. The lift of a rule is defined as the ratio of the observed support to that expected, if x and y were independent. The rule has a lift of. The conviction of a rule is defined as the rule has a conviction of, and can be interpreted as the ratio of the expected frequency that x occurs without y, that is to say, the frequency that the rule makes an incorrect prediction, if x and y were independent divided by the observed frequency of incorrect predictions. In this example, the conviction value of 1.2 shows that the rule would be incorrect 20% more often, 1.2 times as often, if the association between x and y was purely random chance. Process. Association rules are usually required to satisfy a user-specified minimum support and a user-specified minimum confidence at the same time. Association rule generation is usually split up into 2 separate steps. 1. First, minimum support is applied to find all frequent ITEMSITs in a database. 2. Second, these frequent ITEMSITs and a minimum confidence constraint are used to form rules. While the second step is straightforward, the first step needs more attention. Finding all frequent ITEMSITs in a database is difficult, since it involves searching all possible ITEMSITs, item combinations. The set of possible ITEMSITs is the power set over and has size, excluding the empty set which is not a valid ITEMSIT. Although the size of the power set grows exponentially in the number of items in, efficient search is possible using a downward closure property of support, also called anti-monotonicity, which guarantees that for a frequent ITEMSIT, all its subsets are also frequent, and thus for an infrequent ITEMSIT, all its supersets must also be infrequent. Exploiting this property, efficient algorithms, for instance, a priori and a CLA, can find all frequent ITEMSITs. History. The concept of association rules was popularized particularly due to the 1993 article of Agrawal and others, which has acquired more than 6,000 citations according to Google Scholar, as of March 2008, and is thus one of the most cited papers in the data mining field. However, it is possible that what is now called association rules is similar to what appears in the 1966 paper on GUHA, a general data mining method developed by Peter Harjic and others. Alternative measures of interestingness. Next to confidence, also other measures of interestingness for rules were proposed. Some popular measures are all confidence, collective strength, conviction, leverage, lift, originally called interest. A definition of these measures can be found here. Several more measures are presented and compared by Tan and others. Looking for techniques that can model what the user has known, and using these models as interestingness measures, is currently an active research trend under the name of subjective interestingness. Statistically sound associations. One limitation of the standard approach to discovering associations is that, by searching massive numbers of possible associations, to look for collections of items that appear to be associated, there is a large risk of finding many spurious associations. These are collections of items that co-occur with unexpected frequency in the data, but only do so by chance. For example, suppose we are considering a collection of 10,000 items, and looking for rules containing 2 items in the left-hand side, and 1 item in the right-hand side. There are approximately 1 trillion such rules. If we apply a statistical test for independence with a significance level of 0.05, it means there is only a 5% chance of accepting a rule, if there is no association. If we assume there are no associations, we should nonetheless expect to find 50 billion rules. Statistically sound association discovery, 16.6 left square bracket 17.6 controls this risk, in most cases reducing the risk of finding any spurious associations to a user-specified significance level. Algorithms. Many algorithms for generating association rules were presented over time. Some well-known algorithms are a priori, ACLAR and FP growth, but they only do half the job, since they are algorithms for mining frequent EMSITs. Another step needs to be done after to generate rules from frequent EMSITs found in a database. A priori algorithm. A priori algorithm. A priori is the best known algorithm to mine association rules. It uses a breadth-first search strategy to count the support of EMSITs, and uses a candidate generation function which exploits the downward closure property of support. ACLAR algorithm. ACLAR is a depth-first search algorithm using set intersection. FP growth algorithm. FP stands for frequent pattern. In the first pass, the algorithm counts occurrence of items, attribute value pairs, in the dataset, and stores them to header table. In the second pass, it builds the FP tree structure by inserting instances. Items in each instance have to be sorted by descending order of their frequency in the dataset, so that the tree can be processed quickly. Items in each instance that do not meet minimum coverage threshold are discarded. If many instances share most frequent items, FP tree provides high compression close to tree root. Recursive processing of this compressed version of main dataset grows large item sets directly, instead of generating candidate items and testing them against the entire database. Growth starts from the bottom of the header table, having longest branches, by finding all instances matching given condition. New tree is created, with counts projected from the original tree corresponding to the set of instances that are conditional on the attribute, with each node getting some of its children counts. Recursive growth ends when no individual items conditional on the attribute meet minimum support threshold, and processing continues on the remaining header items of the original FP tree. Once the recursive process has completed, all large item sets with minimum coverage have been found, and association rule creation begins. 18.6. GUHA procedure ASOC. GUHA is a general method for exploratory data analysis that has theoretical foundations in observational calculi. 19.6. The ASOC procedure, 26, is a GUHA method which mines for generalized association rules using fast bit strings operations. The association rules mined by this method are more general than those output by a priori. For example, items can be connected both with conjunction and disjunctions, and the relation between antecedent and consequent of the rule is not restricted to setting minimum support and confidence as in a priori. An arbitrary combination of supported interest measures can be used. Opus search. Opus is an efficient algorithm for rule discovery that, in contrast to most alternatives, does not require either monotone or anti-monotone constraints such as minimum support. 21.6 initially used to find rules for a fixed consequent. 21.6 left square bracket 22.6 it has subsequently been extended to find rules with any item as a consequent. 23.6 Opus search is the core technology in the popular magnum opus association discovery system. Law. A famous story about association rule mining is the beer and diaper story. A purported survey of behavior of supermarket shoppers discovered that customers, presumably young men, who buy diapers tend also to buy beer. This anecdote became popular as an example of how unexpected association rules might be found from everyday data. There are varying opinions as to how much of the story is true. 24/6 Daniel Powers says, 24/6. In 1992, Thomas Blishak, manager of a retail consulting group at Teradata, and his staff prepared an analysis of 1.2 million market baskets from about 25 Osco drugstores. Database queries were developed to identify affinities. The analysis did discover that between 5 o'clock and 7 p.m., that consumers bought beer and diapers. Osco managers did not exploit the beer and diapers relationship by moving the products closer together on the shelves. Other types of association mining. Contrast set learning is a form of associative learning. Contrast set learners use rules that differ meaningfully in their distribution across subsets. 25/6. Weighted class learning is another form of associative learning in which weight may be assigned to classes to give focus to a particular issue of concern for the consumer of the data mining results. High-order pattern discovery techniques facilitate the capture of high-order, polythetic, patterns or event associations that are intrinsic to complex real-world data. 26/6. K-optimal pattern discovery provides an alternative to the standard approach to association rule learning that requires that each pattern appear frequently in the data. Generalized association rules. Hierarchical taxonomy, concept hierarchy. Quantitative association rules. Categorical and quantitative data. 27/6. Interval data association rules. For instance, partition the age into 5-year increment ranged. Maximal association rules. Sequential pattern mining discovers subsequences that are common to more than min subsequences in a sequence database, where min sub is set by the user. A sequence is an ordered list of transactions. 28/6. Sequential rules discovering relationships between items while considering the time ordering. It is generally applied on a sequence database. For example, a sequential rule found in database of sequences of customer transactions can be that customers who bought a computer and CD-ROMs, later bought a webcam, with a given confidence and support, later bought a webcam, with a given confidence and support, later